Hi everyone. In this video we are going to continue from the last video. In the last video we went over the model, how the model is loaded, etc, etc. In this video we are going to go through the process of constructing our design model for optimization in MSC Nastran. And before I get started, as always, if you have a question, if you want more training on optimization, feel free to send me an email at this email address and I'll definitely get back to you. In the last video, we went through our optimization problem statement. What is our objective? What are our constraints? And what are design variables? So by this point, I'm assuming you already have a Nastran PDF file. For example, this cantilever plate is contained in a PDF file in the folder on my desktop that you see here. This model PDF has a description of the entire model, has the loads, the elements, the grid points, all of that stuff. This file is what we have to convert to solution 200 for Nastran. So now let's go through the process of doing that. We're going to select all the text in the file and we are going to paste it into this web app. This web app is going to facilitate the process of converting this solution 101 file to a solution 200 file. Again, take the text, paste it in this box, and click Identify Design Properties. In this next table, you get a summary of everything that can be set as a design variable. There are 4 thicknesses, the Young's modulus, the Poisson ratio, and the density can be set as design variables. Here, I want to set the 4 thicknesses as design variables. So I'll select thickness 1, 2, 3, and 4. And in the next table, I have my design variables created for me. Now I have to specify the limits of the design variables, which are the thicknesses. Here I'm saying that the thicknesses are to be between 0.01 and 0.5. So let's go ahead and type in 0.01 here. And then 0.5 for the upper bound. And that completes the creation of the thickness, or the design variables, I should say. Let's go ahead and move on to the objective. In the top navigation bar of the web app, you can click on objective. In this section is where we define our objective, and here we want to specify the mass or the weight as the objective. So let's go ahead and select that, and let's go ahead and set it to minimize, and let's go ahead and move on to constraints now. This is where we want to define 2 constraints. One constraint is for the displacement, and the second constraint is for the von Mises stress. Let's go ahead and set the displacement constraint. When you're in the constraint section, you have a long table of constraint types you can set. Here we want to set the displacement as a constraint type. So click on the plus icon one time. And in the next table is your new constraint that you have to now configure. So let's go ahead and look at this for a moment. We want to constrain the displacement in the z direction at grid 208. So for the displacement component, which would be this box, and here let me go zoom in for you. We will type in a 3 for the Z component, and for the grid we would say grid or node 208. Grid 208 would be one of the nodes in this corner section here. Let me see if I can display it, or here I'll do that. Here we go. 208 would be this node that you see here. Let me zoom in a little bit more. So it's basically a node at the tip of the cantilever. Let's go ahead and zoom that out. And for our bounds for the constraint, we are saying that the deflection can be between -3 and 3. So let's type in -3 here and 3 in the upper bound. And let me point out something that's happening in the web app that may be very subtle. Here on the right, you get the output. Let's go through this for a moment. For every constraint type, you create 2 pairs of bulk data entries for MSC Nastran. You create a DRESP1 and a deconstraint entry. And that's here as a preview as to what's going to be written out later. For the objective, you just need a DRESP1 entry. For the variables, you need pairs of dvpro1 and desvar entries for each design variables. And here you saw how easy the web app was to generate these entries. Let's go back to creating our design constraints. We also have to create stress constraints for the von Mises stress and the cantilever. What we want to monitor is the stress in the upper and the bottom fiber of this cantilever plate. So let's go through the process of doing that. In the same list of constraint types, let's go ahead and select the plus icon to create a stress constraint, and that's now listed here in the bottom. Let's go ahead and type in P shell for the property type. For the elements IDs, I believe, here, let's go ahead and look at this for a moment. Let's actually look at the model. The model will tell you what the P shell IDs are essentially. So let's go ahead and look at that. So the 4 sections correspond to P shell 1, 2, 3, and 4. Those are the IDs we want to use here. We want to say apply this stress constraint to P shells 1, 2, 3, and 4. And for the von Mises stress, the upper limit will be 36,000. So let's go ahead and type in 36,000. And then again, here on the right, the output is automatically generated for you. Again, the constraints come in pairs, a DRESP1 and a deconstraint. And there's one last box we have to fill in, the stress item code. Elements can have various quantities. They can have forces in their local X, Y, Z coordinates. They can have stresses in the element coordinate system. They can even have strains. So we have to specify a stress item code that corresponds to the von Mises stress of that element. Now to do this, we have to refer to a chapter in the quick reference guide for Nastran called item code. So let's go ahead and navigate to that. In chapter 6, there's a section for C quad 4. Here you see it as I highlighted. Navigate to the C quad 4 144 element. Here is a summary or a list of all the item codes 1, 2, 3, 4 that you can specify. And here what we want to do is find the item code that corresponds to the von Mises stress of one of the fibers. So here if I go down the list, here I find a von Mises stress corresponding to element item code or item code 11. So let's go ahead and type in 11 here. And you'll notice one special thing about this item code. If we go down the list again, we find a second von Mises stress item code here. And the reason is because if we look back in Patran, let's remember that there is an upper, or rather a top and bottom fiber for this cantilever plate. So there is a von Mises stress at the top and the bottom. Hence, that is why we have a second item code that corresponds to the von Mises stress at Z2. So what we have to do, and keep this number 19, this is the item code for the second von Mises stress. Back in our web app, we have to create a second stress constraint. Essentially identical, it's the same P shell, same IDs, and the same upper bound. But this time, the stress item code should be 19. And that completes the creation of the constraints. Now we have to create a constraint group. Later on, where you're creating more complex optimizations, depending on what load cases you have, you might want to specify different design constraints for each subcase. Let's go ahead and do that now. So for the next step, step 3, you can do this in 2 ways. I think I will show you the manual method. Let's go ahead and click on Add Constraint Group. This is where you can supply labels of your constraints to create a constraint group. Here, I want to include R1, R2, and R3 into this constraint group. So let me zoom in on that so you get a better look. So R1, R2, and R3 correspond to the displacement and the stress constraints. So here, let's go ahead and type in R1, R2, and R3. And then we want to apply this to all the subcases. In this case, I only have one subcase, so it's the same as applying it to all the subcases. Now let me zoom out. And now let's go ahead and move on to our exporter. Here, let's summarize what has happened. We have taken this BDF file, we've supplied it to the web app. The web app then converted the solution 101 to solution 200. It added various additional statements to perform the optimization. And the second thing it's done, it's helped you generate your design model. This design model includes all of the entries for your design variables, your objective, your constraints, and your constraint group. So at this point, we can actually download these BDF files and perform an optimization with Nastran. So let's go ahead and do that now. I'll click on Model BDF here and download BDF here. And I've downloaded two files, a design model and a model BDF. So let's go ahead and copy those two files and paste those here on my desktop. I'll create a new folder called Optimization. And then here I'll just go ahead and paste those two files there. And now I can go and start Nastran to perform my optimization. So let's go ahead and navigate to that directory and run the optimization. Okay, our optimization is now complete. Let's go ahead and look at our F06 file very quickly. We want to make sure that we have the message run terminated due to successful optimization. I forgot the statement. Run terminated due to hard convergence at an optimum. This means a successful optimization has been performed. And at this point, this concludes this video. In the next video, I'm going to walk you through the process of using Excel to view the history of your design objective and your design variables using Excel. And with that, I'd like to go ahead and give you a quick reminder. My name is Christian. If you're interested in more training for optimization, if you want me to help you perform an optimization of your own on your own project, or if you want access to this specially crafted web app for Nastran optimization, please feel free to reach me at this email address and I'll definitely get back to you. And again, there is an upcoming video, so definitely watch that after this. Thank you for watching.